I want to simulate fluids. There are two main approaches, using particles, which is called Lagrangian, or using fixed cells, which is called Eulerian. In this video I want to focus on the fixed cell Eulerian approach. The particle approach is fun though, and in Unity is easy to do. I just create a tiny sphere with bounciness 0 and friction 0, and spawn a few thousand of them. I might experiment with particles in a future journey. It's also possible to have a hybrid where particles morph into cells that morph into particles, but I will leave that for future experimentation. There are so many places I want to go that I can't, like inside the Earth, through the Sun, see black holes colliding. I can't do these things in reality, but maybe we can simulate them. In the Eulerian approach, the fluid is represented by stationary cells. Each cell has a single vector which represents the velocity of the fluid in that cell. Let's add some coloured ink to the fluid. The ink flows in the direction of the velocity. This is called advection. I'll talk about how we can implement advection a bit later. To simulate places I cannot go, I feel a useful first step is, can I simulate a simple fluid? No viscosity, no air, and I'm going to keep to 2 dimensions. So that's my goal for this video, and I'm going to use GPU shaders because shaders are fun. Let's make the colour sources persistent. And then I'll add a drop of each colour. Let's increase the resolution to 30p and turn off the arrows. I started this journey by watching some videos by Matthias Müller, who is physics research lead at NVIDIA. I read through Joss Stam's Real-Time Fluid Dynamics for Games. I feel that Brian Trevathan's thesis, Physically Based Simulation for Computer Graphics, gives an excellent survey of fluid simulation techniques. I couldn't understand his maths at first, so I spent several weeks watching videos on maths by Comitant, Elucider and Dr. Payam.
In French, la place means the place. So you know you're in the right place.
It feels a little static, so let's add some noise to the colour. This gives a little sensation of movement. We can actually increase the resolution more to 480p. This is pretty fun, but if I go back down to resolution 8p and turn the arrows back on, we can see that whilst the fluid is technically moving because we have velocity arrows, but the arrows themselves are not moving. The fluid movement is not moving itself. And look, I can track these arrows so they're all pointing to the same cell, more or less. So that means we've got fluid flowing into this cell and no fluid flowing out. So the fluid is either being destroyed or it's being infinitely compressed like a black hole. But generally, it's not behaving like a typical fluid. There are 2 things that we need to make the simplest fluid simulation that I'm aiming for in this video. One of these things is conservation of mass, incompressibility. When fluid enters a cell faster than it leaves, this is called negative divergence. And when fluid leaves a cell faster than it enters, this is called positive divergence. So here we have white fountains that represent matter being created, and black whirlpools represent matter being destroyed. Now, to make our simulation, we need to clear this divergence. Joss Stam used some fancy maths for this using Helmholtz decomposition, but the maths was hard for me to understand, and calculating the curl-free field needs an iterative approach. Matthias Müller proposes an approach that does still need iteration, but I find much easier to understand. We do need to change representation slightly though. Instead of storing the velocity at the center of each cell, we're going to store the velocity at the edge of each cell. It's a little less intuitive to look at, but calculating divergence is now really easy. All we have to do is add up the velocities flowing out of the cell and subtract the velocities flowing in, and that's our divergence. In my shader code, I take the velocity flowing out of the right hand side, add the velocity flowing out the top, and subtract the velocity flowing into the left hand side and into the bottom, and that's the divergence. To clear this divergence, what Matthias proposes is we take the divergence, divide it by 4, like the number of edges of the cell, and subtract that from each of the edge velocities. This will immediately set the cell's divergence to 0. So I can click on these cells to clear their divergence. When I clear the divergence for a cell, I increase the divergence of its neighbours, but that's okay, I can just keep clicking. It's a little like trying to put a screen protector on your phone and there's a bubble of air trapped and you're pushing it around. But in our case though, the bubbles will go away eventually if we click enough. In my shader code, each thread takes the divergence of the cell, divides it by the number of fluid neighbours to form delta vel, then subtracts delta vel from each of the edge velocities. The divergence of the cell immediately becomes zero. Clearing divergence is also called projection, which is why this function name starts with the word project. Let's go back to showing the center velocities because I think they're easier to understand. Rather than clicking by hand, I can get the computer to click for me. And I can speed this up a bit. If I clear this and draw a single upwards velocity, the projection will gradually produce arrows flowing backwards so that the flow loops around. Of course, I didn't spend 4 weeks writing shader code just to run projections cell by cell, but there's a problem. Threads on a GPU are a little like rowers in a rowing team. They move together in lockstep. They all run the same instruction at the same time. This means that if multiple threads try to update the same value, only one will succeed. On the left, we have some threads symbolized by spirals. Next to each thread we have an input color. I can connect an input color to an output color using an arrow. When I click step, each thread adds its input color to each connected output color. What happens if I connect two inputs to the same output? We might expect the inputs to mix to form a blend, but actually only one thread succeeds. The other thread's update is ignored. Here is the shader code for this demo. Each thread runs this function once, each with its own thread ID. Each thread loops over the outputs. If there is a connection from the thread's input to an output, then the thread adds its own input to that output. When using a shader, each output value should be updated by only a single shader thread. Going back to clearing divergence, when I cleared the divergence for two adjacent cells, each of them modifies the velocity of their shared edge. So to clear the divergence of two neighbor cells, we need to run their cell updates in sequence. On a shader, we want to run many threads in parallel, so this sounds impossible. There's a solution though, which Matthias shows, which is called red-black gauss-seidel. If you look at all the cells I'm selecting, none of these cells have shared edges. So I can update these cells together in parallel without right conflicts. And then we can select another set of non-adjacent cells and clear those. There are 4 sets of such non-adjacent cells in total, so in 4 passes we can update all cells. It's also possible to use only 2 passes, but I get slightly better frame rate using 4 passes. Let's run projection continuously. Alright, you can't see it, but it's running projection. So now when I drag velocity around, the other flows adjust immediately to keep divergence 0 everywhere. What this means is that the velocity loops around back to where it came from. It doesn't just vanish into nowhere or be created from nowhere. If I try to change the flow to point upwards, somewhere there's going to be downwards flow. Let's add some persistent upward flows. So now we have some very strong backflows like riptides in surf. Let's bump up the simulation resolution to 80p and use color to show velocity. I'm using HSV color to depict the velocity. The hue shows the direction. There's a color wheel here. Black is stationary, and then the brighter the color, the faster. These spots are yellow, meaning they are upwards velocity. This blue color shows downwards motion. This red color shows motion to the right, and this cyan shows motion to the left. Because projection is running, we get these gorgeous color gradients as the flows loop around. But we don't really see movement, so let's try switching to colored ink mode and add some colored ink. And we can drag the velocity around, which is pretty fun. But we still don't really see movement because the ink reaches a steady state. So let's add some color noise. The noise shows movement, but it adds a bunch of extraneous color around the edges, so let's add some decay to the ink. Alright, so we got rid of the extraneous color and we have some kind of sensation of movement, but now our actual color kind of faded a lot. So what we can do is we can increase the advection speed. So let's bump up the advection speed to about 140, and then I can drag the velocity around. Alright, so it's not actually clear what is different compared to not having projection on. Let's reset, turn off projection, and draw a single line of upwards persistent velocity. If I switch to the HSV view, we can see that there is no velocity except for that line. Now let's turn on projection. So now the whole simulation fills with a beautiful color gradient effect, and this means that everywhere has some velocity now. Let's go back to ink color view and draw some ink sources. Alright, so we've definitely got movement now, and it seems plausible that we're enforcing incompressibility. But does this look right? Does fluid normally spin around like this? Like maybe in a food blender? But what we have here is a single source of directional velocity, like a hairdryer or a fan. Wouldn't we expect that fluid to have momentum and carry on in a straight line, like water out of a tap? We would. To add conservation of momentum, what we need is to add advection of velocity. We saw advection before for the coloured ink. Advection means moving things in the direction of the velocity. Advection of velocity means we're going to move the velocity itself in the direction of itself. This seemed a bit mysterious to me, but if we switch to using particle representation, it becomes a bit more obvious. In the case of particles, each particle has a velocity, and the velocity of each particle moves with that particle. If I add Eulerian cell colours, the cell colours also move with the particles in the direction of the particle velocity. This is especially obvious for the particles on the edges. So we need to add this velocity advection to our Eulerian cell-based simulation. Let's change back to low resolution and turn the arrows back on. So if I move the arrows so their tail is in the cell centres, then the arrows point to where the velocity needs to move to next. So what we could do is take the velocity from a cell and move that along the arrow to the head of the arrow and somehow spread the velocity over the nearby cells. But there's a problem. If you look at this cell here, there's multiple arrows pointing into it. In my shader I want to use one thread for each cell, one thread per arrow. So two arrows pointing to the same cell means that we have two shader threads updating the same value. From the demo earlier, we saw that this is impossible. One of those updates will fail. But what we can do is change from a push to a pull. Let's go back to the thread update demo. We can assign each thread to an output instead of to an input. Each thread will pull colors from the inputs. This way each output is only updated by a single thread. If we have two inputs pointing to the same output, that works just fine. Switching from a push to a pull can also help us run advection on a shader. Here is the shader code for this demo. Each thread loops over the inputs. If there is a connection from an input to that thread's output, then the thread adds that input value to its output variable. Finally, the thread writes its output variable to its output, and this works okay. So let's use this pull approach for advection. I can slide the arrows backwards so that they point into each cell rather than out of each cell. Then each thread can pull the velocity from the tail of its arrow into its own cell. And this will run just fine on a shader. Unfortunately, the tail of each arrow won't usually lie exactly over a single cell, so we will need to interpolate over the four nearest cells. Here is my shader code to interpolate between four cells, given the index of the bottom left cell and a lambda interpolation vector. The actual code has a bit more bounds checking, but it's otherwise similar. The advection is a bit fiddly because we are not actually storing the velocities at the center of each cell, but rather the staggered velocities at the edges of each cell. Debugging this took me quite a while, but I got there in the end. Without projection, nothing happens when I turn on advection and draw some velocity. This is because we are doing a pull. The cells doing the pull have zero velocity, so the length of the arrow to the source cell is also zero. Each cell pulls from itself. Since each cell has zero velocity itself, then it pulls zero velocity from itself and nothing changes. If we turn on projection, this problem goes away. The projection smears non-zero velocity everywhere with this beautiful gradient color effect. Even if the velocity is near zero, it's still enough to kickstart the advection process. It's not enough to only apply a projection though. With only projection, the fluid does not stream forward in a straight line. We just get small localized loops of fluid flow. So there's no divergence, but it's basically static. With both projection and advection, I feel it looks quite nice. Having to turn on projection in order to test advection made debugging really hard. It was hard to know if bugs were in my projection code or in my advection code. And let's be honest, bugs were everywhere. Really, I want to be able to test projection and advection separately. This will make debugging easier. So let's think about trying to run advection without projection. The problem is, without projection on, the advection does a pull from zero velocity and nothing happens. So how to test? So one option is to click somewhere and drag backwards in the opposite direction of the velocity. Since my mouse position is supplying velocity, this velocity flows forward from my mouse, and so we get a stable line of velocity. When I release the mouse, the velocity then advects away from where my mouse was. I thought that adding noise to the velocity might help, since then the velocity would be non-zero everywhere, and it kind of does. But it turns out the direction of the velocity matters, and it's wrong half the time. So let's turn the noise off. What does work is to pre-warm an area with some velocity that's going in the same direction I want to run advection, and then I can advert velocity over that. Still, it's hard to be sure if it's really correct. In the end, I wrote a bunch of shader kernels just for unit testing. This was quite a lot of pain, but at least I could be somewhat confident that my code was working-ish. Let's turn projection back on and then bump up the resolution to 480p. It's a little slow, so let's bump up the advection speed to 140. That seems pretty fluid. I'm going to draw a line of persistent upwards velocity. Alright, so that flows upwards and it hits the ceiling, but what's wrong with this picture? So we've got this huge block of fluid moving upwards and it's hitting the ceiling. The ceiling is solid, the fluid cannot go through it. So the fluid's vanishing, like there's no fluid coming out the sides. So this is violating conservation of mass, but we already have projection. Shouldn't projection fix that? Well, when we added projection, we saw that we need to iterate the projection step, and I'm not. I'm just running the projection step once in between each advection step. It turns out that the number of projection iterations is important, and we need quite a few more than one in between each advection step. So let's try 3 and 5, 7, 10. So increasing the number of projection iterations is definitely helping. What we need is for the information from the center of the upflow to get to the edge of the upflow before we take the next advection step. Each red-black gauss-seidel iteration communicates information about 2 pixels each time, like no more than 2 pixels. And I guess we've got like 50 to 100 pixels here, so we're going to need at least 50 iterations or so. So let's try 50, and let's try 100. Alright, that's looking a lot more convincing, and something I like is that now we see some nice turbulence effects. I think turbulence is really fun and interesting. I think it looks much more convincingly like a fluid with turbulence in. And I didn't have to do anything fancy to get the turbulence. I just applied a few fundamental laws of physics. Conservation of mass, conservation of momentum, incompressibility. I think that's pretty fun. Let's load in some velocities and colors I drew earlier, and let's dab on a few spots of green ink. This is running at 50 frames per second on my Macbook Air. I think this looks quite convincing as a fluid, and I'm pretty happy with how this is looking. What I want to look into next is simulating the inside of the Earth, the Sun, and black holes. If you're interested too, please consider subscribing. If you liked this video and you want me to make similar videos, please consider encouraging me by clicking like. Cool, see you.